So, in today's lecture, we will be solving some example problems on impulse response and arbitrary loading. We will apply the concepts of convolution integral and impulsive response to solve these problems. So, the first problem, a very conventional problem that we will be dealing with, is the response of a damped single degree of freedom system due to a step load. So, the most of us are acquainted with a step loading. The step load actually starts at t0 at t equals to 0 and then goes to an unit value or certain magnitude p. So, this shows the step load. So, with a magnitude of p. So, let us try to write down the equation of motion for this. Which is m u double dot plus c u dot plus k u is equal to f t. F t is nothing but p into a step. So, this is the symbol that I have been using for step load. Now, let us see how we can solve the solve to obtain the response of the system under this step load. So, we know that u t, assuming initial conditions, are 0. So, we are considering that the initial conditions are 0, assuming the initial conditions to be 0, that is initial displacement is 0 and initial velocity is 0. So, the response can directly be written in form of a convolution integral or Duhamel's integral in this form. So, 0 to t and then I have f tau into h t minus tau into d tau. Now, f tau is p, it is constant after t equals to 0. So, this can actually be written as 0 to t p into h t minus tau into d tau. I also know the expression of h t minus tau. So, if I write this, I am in a detailed form, I will get this as p by m omega d to the integral from 0 to t e to the power minus zeta omega n t minus tau into sin omega d t minus tau into d tau. So, let me call this integral as I. So, u t is nothing but p by m omega d into I, where I is this integral. This integral I am representing as I. So, let me now try to evaluate this integral I. So, the integral I is 0 to t e to the power minus zeta omega n t minus tau sin omega d t minus tau into d t. So, the best way or the easiest way to solve this integral is integration by parts. So, let me do integration by parts. So, if I do integration by parts, I am going to get this as e to the power minus zeta omega n t minus tau. So, if I do integration by parts, I am going to get e to the power minus zeta omega n t tau by 1 by omega t. This can actually be written as, when tau is equal to t, I have this as 1 by omega d and then minus e to the power minus zeta omega n t . For t, this goes to 0. So, I am left with minus So, this is going to be, so I get back the same integral I. So, if I write further, then I get I 1 plus zeta square omega n square by omega d square is equal to 1 by omega d into 1 minus So, if I evaluate this, this is going to be 1 plus zeta square 1 minus zeta square is 1 by omega d So, this actually becomes 1 by zeta square. So, this can be written as 1 by zeta square. So, eventually this can actually be written as 1 minus zeta square. Therefore, ut, which is nothing but p by m omega d into I, can actually be written as 1 minus zeta square by m omega d square into 1 minus e to the power minus zeta omega n t to cos omega d t plus zeta 1 minus zeta square sin omega d t. So, this can further be simplified. So, omega d square can actually be written as omega n square into 1 minus zeta square. So, this cancels out. So, this can finally be written as 1 by m omega n square, sorry, p into 1 minus e to the power minus zeta omega n t into cos omega d t plus zeta 1 minus zeta square sin omega d t. So, this is the expression that we get. So, this is the response of the single degree of freedom system of S of due to step load. So, let me just plot this response. So, if I plot this response, I can see that let this be ut and this be time. Let me first draw a line which corresponds to p by k. K is again nothing but p by m omega n square. So, now what does p by k represent? P by K represent nothing but the static displacement, equivalent static displacement of the single degree of freedom system, equivalent static displacement due to a load, a static load P. Now, with this reference line, let me draw the response u t. So, let me look into the response u t, the expression of the response. So, it is 1 minus a sinusoidal function multiplied by an exponentially decaying function. So, this part of the expression of the response is a decaying sinusoid. So, this is going to be a decaying sinusoid, very similar to the response of a underdamped single degree of freedom system under free vibration condition. So, this is one part of the response. The other part is a constant with p by omega n square. So, if I try to plot this whole response, this is going to look something like this. So, this will go and then oscillate about this p by k line with gradually diminishing amplitude, and finally, this is going to become like this. So, this red line is nothing but u t, and the response is going to eventually get into a steady state response of amplitude p by k, but initially there would be certain oscillation about the p by k line, and this oscillation will gradually decay and it will eventually become almost p by k. This kind of phenomena must have been observed by many of you all. So, suppose I take a beam, a cantilever beam, and then suspend a certain load at the tip at t equals to 0. So, this kind of loading is going to mimic a step load. So, at t equals to 0, there is a certain application of load, which is the weight of the mass suspended, and that mass is going to stay there. So, this form of loading is a good example of a step loading. You must have observed that when I take a beam and suspend a load at the tip, the beam goes a certain level of oscillation and then it comes to its static equilibrium displacement condition. So, that physical vibration that is observed is exactly captured by the analysis or by the mathematical solution of the equation of motion. So, this shows the beauty of the analysis that we have done, which exactly captures the physical vibration that is observed. So, with this I will go to a next example where it is slightly more complicated than the previous case. Here I have a step kind of loading, or rather a rectangular loading, which is there till a certain time instant t equals to t e, after which it goes to 0. So, we need to find out the response of an undamped single degree of freedom system due to this kind of loading using convolution integral. I have taken it as undamped just to simplify the calculation, but the solution that we will be doing can be very straightforwardly extended to a damped case. Now, how are we going to solve this system? Let me write down the equation of motion of the system. So, I have m u double dot plus C is not there, it is an undamped system, and that is equal to F t. Now, the force F t is not continuous. So, for time less than equal to T e, the force F t has a constant amplitude of P, and for T greater than T e, the amplitude of the force is equal to 0. Therefore, if I write down the convolution integral or the expression for the response in terms of convolution integral, I can say u t is 0 to t f tau h t minus tau into d tau. Now, for the case when t is less than t e, this expression can actually be written as 0 to t, f t is p, h t minus tau for an undamped case is much more simpler, and it can actually be written as 1 by m. Instead of omega d, I can write this as omega n, because omega d is omega n. Then the exponential term does not stays there, and I have sin omega n t minus tau into d tau. So, this can actually be written as, so let me write in a simplified form, as p by m omega n into sin omega n t t minus tau. This integral is very easy to evaluate, and let us evaluate this integral as 0 to t. Then so if I evaluate this integral, I have p by m omega n square cos omega n t minus tau 0 to t. So, this can be evaluated very easily, and this is going to be p by m omega n square into cos, when tau is equal to t, I have 1, and minus cos omega n into t. Therefore, the response of the system is nothing but p by m omega n square 1 minus cos omega n t, when t is less than equal to t. So, let us now try to find out what is going to be the response of the system when t is greater than t. So, when t is greater than t, then u t should be 0 to t f tau into h t minus tau into d tau. So, this t is greater than t e. So, this integral can be written in two parts. One is between 0 to t e, where f tau is equal to p, h t minus tau is 1 by m omega n sin omega n t minus tau d tau. Please note that the limits of the integral is between 0 to t, because f tau is p only between 0 to t, and from t to a generic t, f tau is equal to 0. So, I have 0 into t minus tau into d tau. So, this of course is going to be 0, and we do not need to evaluate this. So, let us now evaluate this integral. So, that is going to be p by m omega n square into cos omega n t minus tau, the limits being 0 to t e. So, if I evaluate this further, I get p by m omega n square, then I have cos omega n t minus t e minus cos omega n into t. So, this is the response of the system when t is greater than t, and we have already evaluated the response of the system when t is less than t, which was m omega n square 1 minus cos omega n t, when t is less than equal to t. So, if you try to solve this problem using other methods different from convolution integral or Duhamel integral, solving this problem will be very complicated, as in very numerically difficult, but if you adopt convolution integral, the solution is very easy to found. Therefore, these are the examples of cases where or problems where convolution integral proves to be very advantageous. So, with this I will end today's lecture. In next, this is the end of module 1. We are done with single degree of freedom system. From the next lecture, we will start the second module, which will be the multi degree of freedom system. Thank you.